Hello everyone. Today we transition from the fundamental parts of the lecture series on convective heat transfer to applications. So, we will focus primarily on electronics cooling, but wherever feasible we introduce other thoughts and applications as well. But the concepts that we discuss in terms of electronics cooling is applicable to other areas very well as well. So, we will start so the reason for looking into electronics at this point is that electronics industry or the IT industry as such is one of the biggest industry in terms of money making, and for example it makes 4.3 trillion dollars in revenue in 2025, while the hardware associated with IT industry is about 475 billions of dollars. So, that makes it that it's very important, and as you can see that some of the topmost companies in the world are all driven or are IT driven or part of the electronics industry. So, we look into that is the motivation, and the second part is that as a person we also see that so many electronic devices are associated with us itself. Even we ourselves will have a laptop, a phone, smartphone, and these days some smart gadgets, this that. So, you see that on in general 33.5 billion internet connected devices are there, and on average there are each person carries about throughout the world 3.6 devices that are connected to internet. What makes the reason for this increase is the increased need for speed and information and amount of sharing of information and so on. So, that makes the reason now from IT, now we have transitioned to why look into thermal management or the cooling aspects or the convective part of it. We will focus on this set of lectures is the convective, how convective heat transfer is applicable or adopted in cooling these devices. So, temperature effects are felt everywhere in a processor, or you take electric vehicles, batteries, everywhere you see temperature effects are felt. So, all the way from transistors, if you look at the specifics of IT industry, all the way from transistor level, which is on the order of nanometers, to all the way to the data center level or compute systems like a desktop or laptop or anywhere. So, you see that the cooling technologies or the temperatures have to be kept in check, or the temperatures have to be maintained below a certain critical maximum, so that the electronic system can function properly for the guaranteed period and reliably. So, these days previously the chip technology used to be the driving factor for the performance, but these days it is the entire packaging that includes heat sink, electronic power delivery and everything becomes a major factor. And again, if you look at the market size, it is about $14 billion in thermal management hardware alone in 2023, and it is expected to grow at much faster rate as we move towards AI and more advanced machinery that will require more processing capabilities. So, we focus on thermal management, and what is thermal management is the next question. As we discussed previously, there are these devices, the temperature effects are felt all the way from smaller devices like a transistor or a package, and to all the way to the data centers. At the smaller scales where the processors or the power devices are kept in power electronics, the fluxes are extremely high. The heat flux can be as high as 10 to 100 watts per centimeter square, with the maximum temperature to be maintained below approximately 100 degrees Celsius. In power electronics, it can be 150 degrees Celsius or even 175 degrees Celsius. However, the challenge is always to maintain these fluxes within the same roughly these temperatures, maximum temperatures, without hitting these temperatures on a regular basis. Then if you look at a hotspot level, which is even a smaller scale level at a 200 micron scale or 100 micron scale, the fluxes are even much higher, which is 30,000 watts per centimeter square in one of the areas of gallium nitride power chip. So, you see that the power levels or heat flux levels are extremely large at the at the smaller scale or device level. But if you look at the entire gamut or the spectrum of devices, so what we get from a silicon fabrication is that you get a die or silicon die which has internally connected, all the transistors are interconnects that connect all the transistors together to perform in a single unit, and that unit is not yet ready to be powered by the external power that we usually supply from the wall. So, what we do is that we take that and connect it through external solder balls and others to a motherboard from a substrate, and the substrate is attached to a motherboard, and the motherboard is connected to a power from the wall. So, we will discuss these things. So, as you kind of take the motherboard and you put it in a desktop, you get a desktop system. If you put it in a server and you take n number of servers, you get a data center or a supercomputer. So, the power level is in the small scale level, it is the power flux or heat flux that is the challenge. At the data center level or the supercomputer level, it is the power that is. If you can see, for example, the top supercomputer for the last decade from 2011 to 2020, you see that for achieving 400 plus petaflops, people are consuming, the system is consuming 28 megawatts of power. So, that is a lot of power for powering a supercomputer. So, that says that the power, meaning that a technology at that large scale has to be different to dissipate heat, while the technology that is needed at the transistor level has to be different to dissipate the high fluxes. So, that is the aim or some of the thoughts going into moving forward. We will discuss some aspects of this. We will not be able to address all the challenges, but we will address some of the challenges using the fundamental aspects that we have discussed in this course so far. So, what is electronics cooling in a very simple and straightforward manner is the thermal management, or the objective of any electronics cooling or thermal management is to maintain the device or the die temperature, silicon die or device or the package temperature at or below a fixed value. This fixed value of temperature guarantees a certain performance and reliability of the device, that if the manufacturer proposes 5 years of operational life and delivers a certain amount of speed and throughput, then that should be achieved for the entire 5-year life. So, that is guaranteed through thermal management while dissipating heat to the local ambient. So, there are in a typical laptop or any desktop segment, you see that there is just not hardware alone that works, but a software intervention is also needed to achieve this thermal management objective. And when the temperatures at the die level is small or lower than the critical maximum, which is called the damage limit or shutdown limit, where you see that it is called a reliability limit. If you operate in these zones where low enough temperatures, then like these reliability limit, so you can optimize cooling and the fans can be kept at low speed so that the acoustics are better. So, however, as we increase the temperature, as we go up higher and higher closer to the threshold limit, you see that performance and power management kicks in. What is this? Is this suddenly you see that your phone is slowing down when you are running a lot of applications, or laptop is slowing down as you are running a lot of videos. And what happens is that the speed of the processor is throttled. Essentially, the speed is reduced 1/3, and so instead of operating at, if it is operating at 100 gigahertz or 100 megahertz or some such thing, you go down to 2/3 of it, of the 100 hertz, 100 megahertz. So, you see that 1 gigahertz to 2/3 of the gigahertz. So, something like that is done to reduce, because we will see shortly that this frequency of switching or the speed is directly related to the power dissipated by these devices. So, that is the first level of control that is employed, is to throttle the speed of the processor, so that the power dissipated comes down and such that the temperature of the device is maintained below a certain maximum temperature. If even that operation is not preventing owing to some part failure or some other aging effect. What happens is that you go to the next level, and this is where your laptop shut down suddenly without any proper reason, and it shuts down to prevent the data loss, and that is called the damage limit. And these are the 3 limits that are already occurring or implemented in your hardware. And we will see that we are going to focus primarily on designing these heat sinks or cold plates, whatever that needs to be, and how to manage at a system level, at a desktop motherboard level, the thermal management. So, we will discuss those aspects as part of this course. So, if you look at the dissipation power, how is power dissipated? There are 2 types of power, one is the standby power and the other is the so called active power. Standby power is when the system is non-operational and is left to itself, and there is still a certain amount of power that is lost, and this is due to the transistor sizes becoming very small on the order of tens of nanometers, and that causes that there is some leakage that happens and other reasons. So, active power is what we typically focus in terms of designing thermal management, which is composed of 2 or 3 components. We are just focusing on 2 main components. One is the switching power, and which is given by the switching power is given by this expression alpha times C load. C here is the capacitance of the transistor, and V is the voltage, and F is the switching frequency or the speed of your processor. Alpha is so called activity factor. Activity factor is nothing but the number of transistors that are actually on while performing this operation. So, that is typically called the switching power, and this is the main component that we try to dissipate as heat, and this alpha and CV square times F is primarily occurring, this power is primarily occurring because of discharge of the capacitance that happens in these circuits. These transistors are implemented as switches and valves in the processors or any device. So, as the switching operation completes and dissipates or discharges the capacitance, you dissipate a certain amount of power. So, the second component, which is the parasitic power, which is to be avoided but cannot be avoided these days, is the so called leakage power. Leakage power is because the source and drain of the processors are so close that a certain amount of current is leaking from the source to drain, even if there is a gate voltage applied to it. So, this leakage component of the current component has a very strong or exponential dependence on temperature. This exponential dependence on temperature is a key reason behind one of the big reasons why some of the processors in the earlier days in 2004-5 days, the processor had to be pulled out of the market because there were a lot of thermal management issues. So, this leakage power has a strong temperature dependent, and as you can see, this is approximately given as some function of A is a constant, exponential of gamma is also a constant, and T is the temperature, the absolute temperature. So, the power leakage power has this expression, and what is the why do we need to pay attention to this is that this has a certain potential as you generate heat or the temperature rises. As the temperature rises, power increases because leakage power increases, and as the power increases, temperature increases. Again, the temperature increase causes increased heat generation. So, this vicious cycle continues unless a certain software and circuit level interventions are carried out. If you let it go, then you run into this situation of what is called thermal runaway. This is also common in batteries these days. When we talk from the perspective of lithium ion batteries, thermal runaway is a situation that has to be avoided. And here it is in the form of in processors, it is in this form of leakage currents. There are other reasons in the battery. So, what we run into is that these 2 components have to be managed, and these are the power that a device will produce, and that needs to be dissipated to ambient actively. And as we move forward, as you can see that any thermal component or thermal management requires electrothermal co-design these days. So, one has to But for the part of this course, we are now going to talk about the electrothermal co-design part. We are going to focus primarily on the convective heat transfer and its applications to heat dissipation. So, what is that we are going to design? That is the next question. So, what we talked about is where is the need for this, then we talked about what are the challenges, then we talked about where is the heat generated. Now, we are going to see how to dissipate, what are the conditions or how do we go about designing a heat sink or any cooling solution to the given situation. In typical terms, the power dissipation for thermal design is often called as design power or thermal design power or TDPs. These are quoted in all the data sheets that someone manufactures a processor or any silicon device. They have to quote this TDP, and there are additional things called in terms of transient requirements. There may be a TDC, total design current, and max current and so on, the power associated with those things. But we are going to focus on this TDP and the steady state level, and the steady state level temperature or thermal design power. Now, that is the power that we need to dissipate. Then what is the other boundary condition we need is where is it going to dissipate. Typically air cooling is often used. So, we will focus on air cooling, but all the discussions that we are doing here are equally valid for liquid cooling and two phase cooling and so on. However, for air cooling, the typical temperatures that the ambient temperatures that one takes up for cooling a processor, let us say, is that for desktops you usually assume 38 to 40 degrees Celsius throughout. This is for average temperature over throughout the world. So, if you are designing a product or a heat sink, then it has to have certain ambient temperature. So, looking at the worst case scenario, you take 40 degrees C as the ambient temperature to these heat sink design requirements and so on and so forth. And also altitude, if the system is going to fly, then the density change, or if it is going to be submerged or it is going to be in submarine or some place, the altitude or the density change has to be taken into account. So, these are the primary. So, you have power, you have the ambient, and then you are also specified the maximum temperature that we can. So, that defines the resistance of this. What is the resistance? Is that you have a junction temperature of the device minus the ambient temperature where it is dissipating the heat divided by the power that we need to dissipate. So, that is the thermal resistance that that is required to be met to manage that processor or the package. So, here is an example, typical example where what we call as packaging is that there are more than, this is the thermal part of it, there are much more than the thermal part, there is also the electrical part where the power is being delivered and so on. So, let us for the sake of discussion for this course, we see that this is the die where it is affixed to a package substrate. There is this layer which is now unnamed is the underfill layer, and that is affixed to the package substrate. It has this package substrate is made up of an insulator called FR4 and copper planes. So, there are n number of those planes depending on what product segment. So, it is a composite material and it is anisotropic material, this package. So, it is affixed to this package, and that package is connecting to the motherboard through these solder balls. So, these balls are the way to power the package. So, the electrical power enters through these solder balls and goes into the package and gets delivered to the various components of the microprocessor transistors. So, this arrangement, the heat is now, this is the active side. The heat is from the die is usually expected to be dissipated towards the upper side, which is the heat sink side. The bottom side where it is affixed to the package is usually because the package, the thermal conductivity of the package tends to be very low, on the order of the effective thermal conductivity can be on the order of 0.4 watt per meter Kelvin. So, it can be largely treated as an insulator, and the amount of heat that comes down to the motherboard side unless something actively was done is very low. So, if nothing is done actively, then the heat from the die will go only towards the ambient, which is at a much lower temperature. So, this arrangement then requires that the die is first, usually here in this case there is a IHS. IHS is integrated heat spreader. That means what we do is that the size of these chips are usually very small, for depending on what product segment, it can be from all the way from 1 centimeter across 1 centimeter to 4 centimeter across 5 centimeter, so on, going to server boards. So, the heat is usually spread over a large heat spreader, so that the heat is dissipated. However, the thermal contact between the device, the die and the spreader is usually very poor, because they are bare silicon and copper is typically used as spreader. So, that to make sure there is a proper thermal contact, the thermal interface material TIM is used. So, this TIM connects the die to the spreader, and from the spreader again it contacts a heat sink through a thermal interface material. So, as I mentioned before, this package is required to deliver the electrical power to the processor, and that package substrate is next connected to a motherboard, and that motherboard is connected to the wall socket that enables powering of the processors. So, a package in general is, there are two objects to a package, is to protect the transistors from environment and also enables power delivery, on top of it dissipate heat as well. So, that is the role of any packaging in current day scenario. So, moving forward, so there are many number of, as we discussed, you can look at it from levels of packaging. The first packaging is what we call here as the package, solder ball and the die. Then the package is mounted with the heat sink, and it is connected to a PCB or the motherboard. Then this PCB is assembled into a box like this, and you get a system level. So, these are some 3 levels of packaging, and as you can see, this is an example of a laptop, that there are multiple modes of heat transfer that is expected to happen. Here is a centrifugal fan, there is a solid state drive, this is optical drive, hard disk drive, and you have processor. This is the memory device, this solid state drive here is a memory device. The CPU is here, the graphics card is there, and there is a fan and a heat sink. So, this fan and the heat sink is the primary mechanism for heat to be removed from all these power generating devices that are mounted on this. So, this fan pulls the heat, and there is usually a heat sink that is placed at this exit vent, and it pushes it out. And you can see in any of your laptops that there is a vent, and if you put your hand on the side, there are 2 vents or 3 vents depending on how the design is. One is to pull the air in, the other one is to push the air out of the system. So, as you can expect, there are 2 or modes of contact or heat transfer modes, that is the contact mode, which is diffusion and convection, and the non-contact mode, radiation. All these modes of heat transfer are important, and we cannot just focus only on convection, but we need to focus both on the diffusion, that is the conduction part, and the convection part, and also the radiation. Especially if we are talking about a smartphone, then the cooling there is primarily by radiation and natural convection. So, moving forward, this is another example of the same laptop, which is flipped. So, here is the example. We saw the back side of the laptop, here it is the front side. You can clearly see how this is the processor, and it is mounted with this so called ILM or the loading mechanism, and the processor is held, which is a LGA, line grid array package, and it is kept in its socket, and this is the thermal interface material that is used, and a heat pipe is connecting to this, and a heat sink is mounted. So, what this is, why this arrangement is that you can't mount a heat sink right on top of it, because in a laptop you do not have space on top of it. So, this is called remote cooling. You remove the heat through the heat pipe and into this heat sink. and move this using what is called heat pipe, and the heat is transported from this location to this location where a heat sink can be mounted and a fan can be mounted, and the fan pushes the air out and comes to the exit, the hot air exits the system. So, these are this is one classic example, but there are many such systems that one can look into. As I discussed, there are multiple concepts of resistance that is involved here. One we will talk about in general is that in electronics industry, one is more focused on the maximum temperature, not the average temperature. Average temperature is what we discuss from a thermodynamic perspective when we are discussing class and developing thermal resistance networks. We usually talk from an average temperature perspective. However, in electronics, one is more focused on the maximum temperature. This is the temperature we should not exceed a certain maximum temperature. This max temperature has to be kept below the critical maximum for reliability purposes. So, one defining a resistance, one usually defines based on this maximum temperature, which may be a point temperature, not an average temperature of the entire die. So, point temperature minus the ambient temperature divided by the power dissipated by. For example, this is a situation where there is no integrated heat spreader, there is some heat source mounted on the bottom of a heat sink. This is a heat sink fins, and this is the base of the heat sink, and how heat is dissipated. So, what you encounter is what is called spreading. Whenever heat flows from a smaller area into a larger area, there is something called spreading resistance that one encounters. Spreading resistance is that the heat does not spread immediately into the entire area. If the sizing, if the thickness of the spreader is not optimum, then the heat will stay as is shown here like this, meaning that the temperature profile will have a maximum, and even at the bottom plane the temperature is still has a peak and has a bell curve type situation. If it were to be spread uniformly, you will get a flat line like this. The spread temperature at the bottom line will see same as the average temperature. However, if the sizing, because you can't put big copper spreaders, the spreaders have to be optimized, because otherwise the weight of the product goes up. So, in order to manage all these things, one has to encounter the spreading resistance as well, and this is how a typical resistance is developed. And R max, there is R max is the temperature difference between the maximum temperature and the average temperature of the base of the heat sink, and then the spreading resistance and the bulk conduction resistance, which is L by Ka that you would have encountered in any heat transfer class, and the convective resistance, which is 1 by H. H is the heat transfer coefficient and S is the surface area from where the heat is dissipated to a moving fluid. Ha is the convective resistance. So, you encounter a series of resistances: spreading resistance, conduction resistance at the base of the heat sink, and convective resistance of the heat sink. So, we will look into some aspects of these, and this is the last part, and where the resistance is again dictated as some temperature, hot temperature minus cold temperature divided by Q, and if using average wall temperatures, then we can define L. If L is the thickness of the wall, K is the thermal conductivity of the wall material, A is the cross sectional conduction wall cross sectional area. The contact resistance is the resistance that occurs when two metals or materials are brought together. This is very sensitive in industrial applications, and the contact resistance is usually empirical in nature, and it is recorded in textbooks and tables and so on. So, the convection resistance, as I discussed, it is 1 by this, and also you can have radiation resistance. For now, we will not discuss much about the radiation resistance, and it can be treated in a simple fashion like this, or through 1 by HR, radiative heat transfer coefficient, times this sigma times epsilon times 4 times T average cube becomes radiation heat transfer coefficient, and then you can write this resistance.